just stared at a really complex machine, maybe a car engine or a big robotic arm, and just wondered, how does it all work so perfectly together? Well, behind every single one of those gears and pistons, there's this hidden, almost elegant mathematical language that can actually predict its every move. And today, we're going to decode that language. This really gets to the heart of the challenge that engineers have been wrestling with for centuries. I mean, how do you go from a simple blueprint, a drawing of metal parts, to a completely flawless prediction of its speed and acceleration at any given moment? That is the big question. And this quest for perfect prediction, well, it created a pretty big dilemma. One that put two totally different ways of thinking on a collision course. So for the longest time, engineers used what's called the graphical method. And that's exactly what it sounds like. They would literally sit down and draw the mechanism to scale just to figure out its motion. Now, it makes sense, right? It's visual, it's intuitive, but, and this is a big but, it's also really slow. It's not very precise, and a shaky hand could throw the whole thing off. So naturally, the hunt was on for a better way, an analytical method that used pure math to get a perfect instant answer every single time. And that brings us to this absolutely elegant solution known as Raven's approach. You can think of it as a special kind of Rosetta Stone, one that translates the physical parts of a machine into the universal language of mathematics. The entire system is built on one incredibly powerful but surprisingly simple idea, the loop closure equation. All it says is this: if you start at one point on a machine and you trace a path all the way around the links back to where you started, all those little arrows representing the parts, the vectors, they have to add up to 0. That's it. This simple rule lets us create a perfect mathematical map of any machine. So how does this translation actually work? Well, you take a physical part, let's say a metal rod, and you represent it as a vector. Basically an arrow with a specific length and a specific direction. Then, using a really clever piece of math with complex numbers, you can capture both the length's length, that's L, and its angle, theta, in one tidy little formula. And just like that, a piece of cold, hard steel becomes a precise mathematical term. It's kind of brilliant. Okay, so we've got our mathematical map, but right now it's just a static snapshot. It's not moving. To really see the machine in action, we need to bring in the big guns, the power of calculus, which is really just the mathematics of change. And here's the cool part. You can think of calculus as a sort of rate of change detector. By taking what's called the first derivative of our equation, we instantly find the rate of change of the position. And what is that? It's velocity. We call it omega. But what if we want to know how fast that velocity is changing? Well, we just do it again. We take the second derivative, and boom, we get the acceleration, or alpha. No guesswork, no drawing, just pure, perfect calculation. Now, this all sounds great in theory, but let's take a look at a couple of real-world examples to see just how powerful this method truly is when you put it to work. First up, we have the 4-bar mechanism. Seriously, once you know what to look for, you'll see this little guy everywhere, from giant construction equipment all the way down to the tiny joints in a robotic hand. Using Raven's approach, if we know how that first input link is moving, we can calculate the exact motion of the other links with absolute pinpoint accuracy. And then, you've got the slider crank. This mechanism literally changed the world. It is the heart and soul of almost every internal combustion engine ever made. It's what turns the rotation of a crank into the back and forth motion of a piston, and analyzing it is absolutely crucial for designing better, more efficient engines. And this is where you really see the magic. Let's say we have an engine with its crank at a perfect 30-degree angle, spinning at 300 RPM. The math tells us the piston is moving at exactly 4.784 meters per second. We get this perfect, non-rounded, incredibly precise number, instantly. And we did it without drawing a single line. So, you can see why moving from drawing pictures to writing equations wasn't just some small step forward. No, this was a complete game changer for the entire field of engineering. It really gave us 3 ultimate upgrades. First, pinpoint accuracy. You get exact numbers, which completely eliminates human error. Second, incredible speed. You can calculate the motion for any position in an instant, something that would have taken hours of drawing before. And third, and maybe most importantly, this is the foundation for all modern computer-aided analysis software that engineers rely on today. You know, the source material puts it perfectly with this analogy. It says the old graphical method is like drawing a line on a paper map. Yeah, it gets you in the ballpark, but one shaky hand could lead to disaster. The analytical method, on the other hand, is like giving a pilot the exact GPS coordinates. It's precise, it's reliable, and it's the bedrock of modern engineering. And all this leaves us with a pretty fascinating final thought. We now have a mathematical key that can unlock the exact behavior of any machine we can possibly dream up. So the only question left is, with this power of perfect prediction at our fingertips, what incredible new machines